Hi, well, I'm Stephen Nesheva, and I'm going to tell you a little bit about how to go about solving the climate modeling problem for an atmosphere-free model of climate. Here's the idea on this game. We've got the sun over here in its shining light, and some part of that sun's energy is being intercepted by the Earth. That's the short wave, or the incoming component of the radiative balance problem of the Earth. And so what we'd like to do is figure out how much is actually being captured by the Earth. And the relevant numbers there are, this number here is called the solar constant. That's the intensity of light coming in, at a single, square meter. Its units are, watts per square meter. In fact, the number is 1367 watts per meter squared. And so that obviously will need to get multiplied by the entire surface, the entire target area that the Earth presents. What's that target area? Well, the radius of the Earth I'm just going to call r, and I know that the area of a circle whose radius is r is just pi r squared. Okay, and that's almost all of it, but there's one more little piece of it, which is that not all of the light that comes and gets intercepted by that target area gets actually captured by the Earth. Some of it is reflected. That's given by the albedo of the Earth, which is 0.3. 30% of the sun's energy just gets reflected off and doesn't get captured by the Earth. So we could just draw it like that. That's the albedo effect. So how do we put that all together for the incoming shortwave term? Well, I've set that up here. The total incoming shortwave energy is going to be that solar constant, 1367 watts per meter squared. This takes into account the fact that some of it gets reflected away. Oh, but I haven't put on here the taking into account the size of the target area, which we've already decided is pi r squared. So I need to put a pi r squared on here. And if you work out the units, watts per meter squared, that gives us watts. Okay, that's all the watts, and a watt is just a joule per second. Okay, so that's the energy coming in. How about the long wave part going out? Well, let's see. I know how to write the long wave. That's if we consider that a Stefan-Boltzmann blackbody emitter. We have an equation, for that, and that's just given by sigma times t to the fourth. Now, this t is the temperature of the surface of the planet. So obviously, the hotter the planet is, the bigger that term is. And but now let's look at the units of sigma. Sigma has units the value is 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth, and that Kelvin to the fourth is what cancels out that t to the fourth term there. So once we do sigma t to the fourth, that is also a quantity that's in watts per meter squared, and so that would correspond to a single point square meter on the surface. That's how much energy goes off in long wave per meter squared. So of course we need to multiply that by the whole surface area of the Earth. And the surface area of a sphere is just 4 pi r squared, r being, again, the radius of the sphere. So I need to fix this formula right here and say, oh, that's watts per meter squared, according to whatever the temperature of the Earth is, times 4 pi r squared. Okay? Good. All right, so now the last bit of this is to say I'm going to insist on radiative balance, because if you think about this, if the temperature of the planet is too cold, then the outgoing long wave will be too small, and it'll have a net imbalance. There'll be more energy coming in from the sun than is getting thrown off in long wave. If that's the case, then the planet will warm up, and so T will get bigger, and T will just get bigger until it's in radiative balance with the incoming solar radiance. So, if we want to find out the point of radiative balance, we need to say that must be equal to that. The incoming must be equal to the outcoming. So I'm going to set I1 equal to I2, and well, algebraically, I hope it's obvious that when I set that equal to that, there's a pi r squared factor in both of them, so that's going to disappear. That means all I need to say is S naught times 1 minus alpha, that's the incoming term, well, without that part, must be equal to sigma times the temperature of the planet to the fourth times 4, okay? And we can divide both of those by 4 sigma, Okay, and that means temperature to the fourth power must be equal to that quantity, and we take the fourth root of both sides of that equation to get an expression for the temperature of the planet, which I'll just let you do, and evaluate the actual temperature.